Portanto, eu não sou um native speaker, um falante natural de inglês, portanto não consigo falar um inglês muito rebuscado, acho que é relativamente fácil de entender. Se eu quisesse complicar para dificultar a percepção, não conseguia, porque não tenho conhecimentos suficientes para isso. So, first I would like to thank to our guest speaker, Thomas Clement from the company VAE. The company has, well, exists almost since the railways exist in Europe, has a lot of experience in fabrication of devices for railway lines, and our speaker works on the engineering department for 25 years and has a lot of experience in this field. The reason why we organized this meeting has to do with the Portuguese situation on the railways. We have, as you know, an historical, the situation for historical reasons. Portugal and Spain have a rail gauge different from the rest of Europe. There were reasons for that in the 19th century. Those reasons don't exist anymore. And now this is an handicap for the competitiveness of our economy, because we cannot communicate directly with the center of Europe. If we want to send some containers to the middle of Europe, they have to change somewhere at the north-south between the Spanish and French border in order to continue on lines with a different gauge. Spain is building a new railway network with European gauge, and in my view, Portugal has two options: or it follows the same way as Spain, or it becomes a railway island isolated from the rest of Europe. And this will be a very good reason for investors not to come to Portugal, for the ones that are here to go somewhere else, which means, for Portugal, means underdevelopment and poverty if we don't solve this problem. So, if we agree on this, that we have to somehow become part of the European railway networks and not just something separated, we have to equate, at least for part of our existing railway network, the transition to the European gauge. There are several ways of doing that. Well, the most clean is just to make new lines with European gauge and close the old ones, but that will be too expensive in many situations. There are situations in which it is justified, but not all of them. And if we, in the existing network, in some lines, depending on the amount of traffic, it may not be economically justifiable to make a new platform for a new line next to the existing ones. And we will need to use the existing platforms. And essentially we have two methodologies for that, which is to use the sleepers with dual gauge, and we have at some time the iberic gauge, and then we change for the European gauge, but there is a period of months in which we have to interrupt the service. Or if we don't want to interrupt the service in those lines, we'll have to have simultaneously trains with different, allow trains with different gauges. And for that situation, to solve that problem, we have this technology of using the third rail that will be helpful in solving many of those situations. It's not a straightforward problem in my view, because both solutions have advantages and disadvantages. And in what regards the rail infrastructure, it's more expensive to make the change using the third rail than using the dual sleepers and make the change completely in one stretch of a line. But on the other hand, for the rest of the economy that uses the railway lines, the interruptions may be deadly in some cases, and they are not an option. For the rail operators, it's also better to have a gradual transition than a sudden transition because of the rolling stock. They have more time to change the rolling stock, so when their rolling stock becomes too old, then they naturally change it for rolling stock of a different gauge. But the point is to discuss these issues and to analyze specific situations. We need information about the advantages and disadvantages of each option. This meeting today is not to decide about any specific line or for us to have an idea about which is the solution for any particular case. It's to try to get knowledge, the technical knowledge that will help us to make that judgment on specific case. And we are going to concentrate on third rail lines and on the devices that we need to put on those lines. So the switches, the expansion joints, and the switches for the third rail, which have different costs, they have operational restrictions, and those are the factors that we'll need to consider when we will analyze these problems in the future. So I want to thank again to our speaker, and the floor is yours, Thomas.
Okay, thank you. It's a pleasure being here and giving a short introduction about dual gauge turnouts. Yeah, my presentation actually consists of two parts. First, I want to give a short introduction of first Alpine, of VAE, where we are placed in the first Alpine group, that you have an idea what we are doing, in which fields we are working, where we are placed all over the world. And actually the second part will be then really a technical part about dual gauge turnouts, focusing in main components really in detail, what can be done, where did we face problems in the past, because we already worked on several projects for dual gauge turnouts, and what could be the solution. And yeah, right at the end, I will come up with a summary and conclusion that will possibly help you to proceed in that project to the next steps. So, just a few slides about us. I'm working for First Alpine VAE Group. As it was already mentioned, we are having 160 years of know-how. The VAE Group is a 100% affiliated company of the First Alpine stockholding company. We are world market technology leader in manufacturing turnouts. We are running production and sales center close to all important rail markets, so that we have more than 40 companies and factories all over around the world. We act as a fully integrated supplier. That means we are able to supply full turnout systems, including locking mechanism, switch detectors, and switch machines. And actually we endeavor to achieve a durable improvement of the ongoing concern values based on continuous profitability and controlled growth. First Alpine Group consists of 4 divisions. The VAE Group is placed in the metal engineering division, and the metal engineering division consists of further 6 business units. I know it's getting a little bit complicated now, but that is actually the last level. And in this business unit, there are the switch products, which is VAE, and as a, let's say, sister company, we have rail products. That is in Austria a rail rolling mill, which is very close to our factory. It's, I think, about 40 kilometers. So most of the rail we are getting from them. And then there is also the welding unit. We are also working quite close together with them in regard of maintenance and repair welding of rail steel, crossing steel, manganese steel, to get these welding procedures, welding materials optimized, which also will be forwarded to the final client in a later stage. So these 3 units, actually, they are working very close together. This map just shows where we are placed all over the world. We have a few factories in North America and Canada, 1 in Mexico. We have 2 in Brazil. We have 3 in South America. We have 1 assembly factory in Saudi Arabia. We have 1 in India. We have 2 in Australia. And also in Europe we have quite a lot of manufacturing places. And The possibly one you might know is one which is in Spain, close to Bilbao, and just behind the French-Spanish border we have one factory which is concentrated on casting manganese crossings. And in addition we have a lot of sales offices in Far East, and these yellow dots, this is our, I would say, relatively new field we are working in. This is existing since about 15 years, where we are producing, we call it components for signaling. So this is hydraulic setting devices, switch detectors, switch machines, and also monitoring systems for turnout, monitoring systems for open track, so hot wheel detectors, flat wheel, hot axle detectors, flat wheel detectors, such things. Some data for the VAE group. We have, with the end of our last business year, so that was end of March 2015, we had almost 2,000 employees worldwide, which is actually spread more than 1,000 in North America, almost 1,000 in Austria, more than 1,000 in Germany, and the rest of 2,000 is spread to the rest of the world.
5,000.
5,000, sorry, yeah. And the chart on the left-hand side actually shows the growth of our turnover over the last 10 years. So last year actually we ended up with 838 million euros. Sorry, turnover sales, yes. Just one slide about products and services, what we are doing. We are very deep involved in the heavy hull market, in heavy hull lines in Australia, in Northern America, South Africa, Brazil, of course. One of the latest projects is the iron ore mine in Mauritania, where we are currently supplying some turnouts, which actually is a really big challenge to install turnout in really desert environment. So this is from point of design, and also in view of the high axle loads they are going there, really a big challenge. We are working for metro and tram turnouts all over the world. We are involved in the high-speed market. We have some projects also on the Spanish high-speed lines, Germany, Austrian, also in Italy, and some projects in Far East, as in China, Taiwan, and Korea. And actually these customers, they are going already up to 350 kilometers per hour on the main line. We also have, for our closer customers, we had set up a kind of a plug and play, just-in-time concept. This is something where we are going to assemble full turnouts in our workshop. We are also assembling switch machine locking detection systems inside in our workshop, setting this to the proper setting values, and these turnouts, they are supplied to a client on special wagons where we are able to place a turnout in kind of 3 main panels on a train. We are working with a kind of tilted wagon for the wider components like the intermediate rail area and the crossing rail, the crossing area, and these fully assembled panels just need to be uploaded on the installation site, put into place, welded together, damped, and the setting system is prepared in a way that it is just need to plugged to the interlocking station. So all the settings of switch machine and everything is done in the workshop. There was done a trial in Austria where they actually closed the track. They removed one old turnout, put one new turnout in with this concept, and the first train was going over this turnout after 8 hours. So that was quite a good approach, and that was actually a kind of a prototype. So in the meantime it already has improved to shorter time. That I actually already mentioned. We are developing switch machine locking systems. We also developed locking and setting systems on hydraulic basis, which are used on high-speed turnouts with very long switch blades. This system can be used up to 10 setting levels, and all these 10 settings levels are only operated by one hydraulic pump right in the beginning of the turnout. We also work on fixed infrastructure diagnostic. So this is a kind of a monitoring system where they can check setting forces on the turnout, where they can check if a crossing nose is already hit by a wheel so that the check rail need to be readjusted. This system can check thermal forces inside the rail so that you have an idea, is there a lot of longitudinal forces coming from the track to the turnout, or compressions. Further, we are working for rolling stock diagnostics. These are the hot axle detectors and flat wheel detectors. And also in addition, we have in Germany, we actually have our own rail grinding machine, which is sent meanwhile through Central Europe and do maintenance and corrective grinding on the open track, and that is also set to be able to do rail grinding in turnout areas. So most of the parts also in turnout areas can be ground with this grinding machine. This is just to have an idea in which fields of railways we are involved. Okay, coming over to dual gauge turnouts. I just prepared I would say a rather simple introduction. Possibly it's easier for discussion. What are the differences to standard turnouts on dual gauge turnouts? So we have an additional rail inside the turnout. Depending on the gauge, the third rail could have different positions inside the turnout. So it could be closer or further off one of the existing rail. And actually, depending on the position of the third rail, there are several different types of turnouts possible. So if you have a right-hand turnout, the third rail is more on the right-hand side, or is it on the left-hand side, makes a big difference, what we will see on the next slide, where I will show all the different types. But in addition, what impact has the third rail on the turnout design? For the switch device, for example, you have to deal with 3 movable components in certain cases. So that means you need to have enough space that 3 switches could move. Not at the same time, but 2 will move always at the same time then. You have additional interruptions on the running edge. That means additional gaps where rails are crossing. That means you have additional crossings. It's not that you have a single crossing as on a standard turnouts. You can end up with 3 crossings in one turnout then, and that might lead to a very complex situation in this area. And also you have a complex ALT solution. ALT stands for actuation, locking, detection, which is switch machine, locking system, and pulse detectors. So also these need to find somewhere some space and place that it can work properly. So coming to the varieties of different turnouts due to the third rail. So combining all possible possibilities, we are ending up with 28 different turnout designs. So and this is depending, is the third rail, is it on the right hand side closer to the right hand, or is it closer to the left hand, or is the third rail just going through the straight, or is it also going, or is it only going through the deviation, or the simpler things, we have a third rail track, the broad gauge is going only in the right, and the narrow gauge is going only in the deviation side. So these are the simpler designs, but having a look on type 1, 2, 3 and 4, this is really complex design, where you can see these letters A, P, C, D, E. They are showing how many and which type of crossings you are using for this type of turnouts. So A, C and D stands for common crossings, and B and E are obtuse crossings, similar to a diamond crossing, which is by its own already a very complex system, and that you have to introduce in such turnout. So these types, the first four, they are giving you the possibility to go with post gauges in the straight and with post gauges in the deviation side. Now I actually want to go a little bit more into detail to have a closer look to the switch device area where the movable parts are, having a closer look to the crossing area, which possibilities or which solutions we can propose, and also in regard of the crossing, because for each crossing check rates are necessary to guide safely through the crossing, what possibilities we have there, and then still some further design issues. So this will go a little bit more into detail, and I'm actually just want to explain it on existing samples we already made in the past on existing projects. So one of the easier things is the gauge combination for standard gauge and narrow gauge, and for broad gauge and narrow gauge. For these two gauge combinations, actually the third rail is far off the outside rail, and for these systems we actually can use an existing switch device, just shifting it into the inside the turnout with existing set of plates, and actually that is working. Even for a type 1, 2, 3, 4, which is actually the most complicated one. There you see it in installation. This is an example which we made for Brazil, CPTM in Sao Paulo, which is a suburban railway. One of the most interesting things is that they are actually combining here a kind of a metro, suburban rail on the broad gauge and on the narrow gauge, and heavy haul. So actually for this project we are dealing with heavy haul application, and also heavy haul trains have much more different wheels as metro trains. So this was also a challenge to find a solution which can be placed in one turnout. So here you still can see switch device is actually the same as here. We are also using separate base plates with a proper fastening, same as is used on the standard track. Another sample is from Switzerland, the turnout Felsberg. This is standard gauge 1434 and 1003 mm. This is also, there is still also enough space between these two rails to have a standard switch device, stock rail and switch plate, including standard base plates, so no special design is required on this turnout. This one shows an example for gauge combination broad gauge to standard gauge, so as it will be in Portugal combined with the Spanish or with the European gauge. This is actually not that easy anymore because the distance between these two rails, so the inside distance between the railhead is only 161 mm. The problem we actually have here is that this switch need to be moved, that the train could go in the deviation side. For standard turnouts, the switch opening is usually 160 mm to achieve a safe run through. As you can actually see here, we need a certain opening that the wheels can go through between the switch and the stock rail. So this opening actually is not possible with this configuration anymore. And we actually decided to go on a reduced switch opening in such a case, just for 110 mm, which is still good enough at the beginning. But what we made over the full length for the switch is that we introduced one more switch machine to provide a proper opening over the whole length, so that we still can achieve a minimum gap in the critical area that the wheels can pass through. Fastening and support of the stock rail and the switch is in this case of course a special design, but we actually have a feasible solution which can be used for such an application. Coming over to the crossing area, for I would say gauge combinations, broad gauge to narrow gauge, so 1600 and 1000 mm, or standard gauge to narrow gauge. Most of the cases a very simple crossing design can be used. So we have there in this case two single crossings behind each other. This is, I would say, kind of a standard design, but as these crossings, they are in a curve, so each crossing is different from the point of the crossing angle, as the angle when you have an intersection of this rail with a curve, you have a different angle when you're intersecting the curve further back with a straight rail. So all are of unique design, but this is actually from point of production and designing not an issue, as these crossings do not require any pattern as for instance cast manganese crossings. Having as an example a turnout with Iberian and European gauge, where you have two rails very close to each other, we were not able to use such designs anymore, because these crossing points, they are coming too close to each other that we are not able to introduce or to use these rail sections to make all these required flares and guiding areas. So in such a case we went for a cast manganese design, so the whole crossing area, which includes two crossing points, is done in a cast design out of cast manganese steel, which is a very common use in railways worldwide, because manganese steel has the property, or the property that it work hardens during operations. So the more often a train is going over the crossing, the harder the crossing becomes, and actually that goes up to a hardness of the crossing of 400 to 450 Fresnel. as a reference,